Have you ever made a decision by playing a game of 20 questions? You start with a broad category and ask a series of yes or no questions, narrowing down the possibilities until you land on the right answer. In the world of machine learning, there's a powerful model that works in a remarkably similar way. This is the decision tree, a fundamental algorithm in supervised learning used for both sorting things into categories, known as classification, and predicting continuous values, like a price, which we call regression. Imagine a tangled web of data points, messy and chaotic. A decision tree takes this chaos and elegantly organizes it into a clear, logical structure, much like a flowchart that leads to a conclusion. To truly understand a decision tree, we need to look at its anatomy, which is surprisingly intuitive. It all starts at the top with the root node, E. This node represents your entire dataset, the starting point of every decision. From the root, we move down to the internal nodes. Think of these as the questions in our game, the points where the data is split based on a specific feature or attribute. Each possible answer to that question leads down a branch. These branches are the pathways connecting our decisions. Following these branches, we eventually arrive at the end of the line, a leaf node. These terminal nodes represent the final outcome, a classification like spam or not spam, or a regression value, like the predicted price of a house. So how does the tree learn to make these splits? The core process is called recursive partitioning. The algorithm AS goal at every step is to ask the best possible question, the one that splits the data into the purest possible subgroups. To measure this purity, we use metrics like Gini impurity or entropy. A group is pure if it contains mostly data of a single class. For example, let's say we want to predict if a fruit is an apple or a lemon. The tree might first ask, is the color yellow? If yes, most fruits in that group will likely be lemons. If no, it might then ask, is the diameter less than 3 inches? This question further splits the remaining group. The tree continues this process, splitting the data again and again at each internal node, creating branches that lead to increasingly pure leaf nodes, until it can confidently make a prediction. Like any tool, decision trees have their distinct strengths and weaknesses. Their greatest advantage is interpretability. The flowchart-like structure is easy for humans to understand and explain, which is a massive plus in fields where transparency is key. They also require relatively little data pre-processing. You don't always need to normalize or scale your data before feeding it to the model. However, they are highly prone to a major pitfall: overfitting. A tree can become too complex, learning the noise in the training data so perfectly that it fails to generalize to new, unseen data. They can also be unstable, meaning small changes in the data can lead to a completely different tree being generated. In conclusion, the decision tree is a powerful, intuitive, and foundational model in machine learning. Its simple, rule-based approach makes it an excellent starting point for understanding how machines can learn to make decisions from data. More than just a standalone model, it also serves as the fundamental building block for more advanced and robust ensemble methods like random forests and gradient-boosted trees, which are workhorses in modern data science. From predicting customer churn in finance to aiding in medical diagnoses, the humble decision tree's influence is widespread and essential.